I really hope this is a short video with regards to so I have not much to say about it, and I hope to talk quickly. Yeah, to hopefully prevent you from getting too bored. pH and indicators, titrations. Oh yeah, so if you're doing a titration, perhaps an acid-base titration, you choose an indicator that turns colors when the equivalence point is reached. You might not know in the beginning what indicator to choose. You may have to do some research. You want to choose an indicator that turns colors right in the area where your equivalence point occurs. For example, if I chose methyl red for this pH, look at the titration curve, I don't think it would work because the methyl red turns colors right in here somewhere. But I really want to detect this pH change, so I might want to use thymol blue. Or maybe even phenolphthalein. But in any case, I want to see when this thymol blue turns from yellow to blue. In other words, where's the big jump in pH? Your indicator should change color right in that big jump somewhere. I said here, always best to pick the indicator with the pKa equal to the pH you wish to change, wish to observe. Wait a minute, pKa, Ka of an indicator? Are you telling me that an indicator itself has a bunch of acid-base nature to it? That's what I'm telling you. I feel silly talking to a computer, but really I'm talking to you. And so phenolphthalein, there's like dozens of indicators. This is the most common one right here. But I wouldn't use phenolphthalein to try to indicate this. Look at this red line. This red line looks for, it's for a polyprotic acid. So one proton on this red line is removed right here, and I might want to use methyl red to indicate that, methyl red. Then moving on up, I continue to add strong base and strong base and strong base. Then I maybe could use phenolphthalein to detect the removal of the second hydrogen from the phosphoric acid. The third one isn't even visible. It's like up here, it's like a teeny bump somewhere. On the other hand, if I was doing a strong acid like sulfuric acid, the first hydrogen at least is removed right here, and there's a huge, enormous jump in pH. And I could use phenolphthalein, or I could use bromocresol purple. What? Never heard of it. Or I could use methyl orange, or I could use methyl red, or bromphymol blue, or cresol red to detect that huge jump, and all those indicators would change color within that huge jump. Same story for HCl. I could use this one, or this one, or this one, or this one, this one, or this one, or this one, or this one to detect that big jump. Let's see some more of those. Question. For the first, I answered the question already, darn it. For the first acidic proton of phosphoric acid, which is this red line here, which indicator might be a good one to use? Well, it wouldn't be this one, and it wouldn't be this one, and it wouldn't be this one, and it wouldn't be, probably not, maybe, but something that changes colors right in that general vicinity of that jump. So methyl red looks pretty good to me, maybe even bromthymol blue. Methyl orange will be pushing it, but it might work, and this bromocresol purple might work as well. This is a kind of a nice colored graph because it shows you the colors those indicators change from yellow to purple, from orange to yellow, from yellow to purple, yada yada. Tried to do that anyway. So we want an indicator, and they all have some kind of acid base, almost all have some kind of acid base nature. Not always true, but with with acid base titration, it's almost always the case. Choose a pKa. We want a what about a? Choose a pKa probably of that indicator molecule. The indicator molecule itself changes when the pH changes, and that's when we see the color change. So here's a weird example. Phenolphthalein is the most common indicator for many acid-base titrations. Usually phenolphthalein is in its colorless form. It's clear, colorless, and the molecule looks like this. But if I add a super duper strong acid and a whole lot of it, and the acid has H+, I could actually break apart this bond right here, adding a hydrogen ion and actually an OH, oxidizing this right in this area to create this structure. This structure is very similar to this structure. If I'm looking at this correctly, I think I break it right here with a strong acid, and that strong acid adds an OH group, or actually adds an OH group to this carbon right here. No, right? Whoa. No, it doesn't have an OH group. It has a hydrogen ion to this right here because it has so many hydrogen ions. Or we can go from this structure to another one. If I increase the pH a little bit, let's see, what does increasing the pH mean in terms of hydrogen ions? Oh yeah, it removes hydrogen ions. So if I were to compare this structure here to this structure here, I see that this hydrogen ion right here is removed as the pH increases. As with increasing pH, I have more and more OH minus, and the OH minus removes the hydrogen ion from this location on the phenolphthalein molecule, and evidently this is pink. And that's a whole nother long story about why it's pink. It has to do with the structure of the molecule itself. If I go even further to a ridiculously high pH, like above pH of 12, that removes even more hydrogen ions. And in particular, it looks like I'm going to break up something right in this area, or actually I'm going to add an OH group right here to, I think this, I'd have to look into that a little bit more, but I see this structure a little bit different than this structure. That's all about the structure of the molecule and extra H plus or losing H plus, adding H plus or losing H plus. If my pH goes down, I'm adding H plus. If my pH goes up, I'm losing H plus. So can you tell how this one's different than this one? Ah, there's a red arrow there. In a low pH with lots of hydrogen ions, I have an extra hydrogen here, versus a high pH where my hydrogen ion gets removed. I have this structure which resonates with this. Hard to believe that this effect can resonate into this, but it's true. So, down here I copied some colors. So the brome crystal green is mostly yellowish greenish in a low pH, and mostly, I guess, this structure looks more bluish in a higher pH, closer to neutral. Here's a good question. If you feel like pausing the video, you could answer it. Which of these structures, Roman numeral 1 or 2, would be more prevalent in a basic solution? Looks like this stuff comes from red cabbage juice, and indeed you can use red cabbage juice as a pH/acid-base indicator. Jeopardy music, and the answer is a basic solution has lots of OH minus, so I'm looking for the structure that has one or fewer hydrogens, and it looks like this has an OH group here, but this has lost its H right here, forcing this structure. There might be a resonance here as well. So I'm going to choose this one as the base. Everything else looks the same if you look at it carefully, but this is the acidic version and this is the basic version, and I suppose they're probably different colors in an acid and base solution. Did we just answer this one? No, different. Okay, different indicator. Azhar in yellow. Which of these structures is common in an acidic solution? Is it Roman numeral 1 or Roman numeral 2? This structure or this structure has an extra one or more hydrogen ions. Aha, it's right there. There's the hydrogen ion. There's it, lost it down here. So this would be the structure in the acidic solution. This is the structure in the basic solution. Bases have lots of OH minus. So OH minus removes that and creates this. And somehow this looks different in color. I forget I could look it up than this. Alright, oh, that's it. Yay, it's done. Go relax. Thanks for watching. See you in class.